So we are not too many, and I'm only used to teaching small set of people because the organization I come from, exactly like you, we don't have undergrad program. We actually also don't have master's program. We only have PhD program. But people can come with after their undergrad, do their master's, and go on to do their PhD. So I'm used to teaching very small classes. But this is a small class, so my accent, it may take some time for you to get used to it. So that's first thing. So first thing you should do is that if you don't understand anything, just stop. Let's not call it I am a lecturer and you are a listener. No, let's make it as interactive as possible. It's not important that we cover all the material because there is no end or dearth to the material, right? So, and if you know something, I say, hey, we have seen these things, so we skip that, move ahead, because there is enough material. And if not, there are lots of board and we can do a lot of things online. So if we make this motto to learn, I think we will learn quite a lot. Okay, so just interrupt. And I see some people, I think they were also for the school, I guess, right? So for you, some of these things you have seen, and it might be boring, but you have to live with it. Okay. So what I'm going to do now is to give you some basics of what these parameterized algorithms are. What are kernels? Like just to give you some perspective in which domain we are going to make these algorithms. And the theme of our lectures is going to be that eventually we would like to see how to use Matroids, which is a very useful tool, object in the current algorithmic world, in designing these parameterized algorithms or some kernels. Okay. First, let me define what is fixed parameter tractable algorithms are. Now, how many of you have done a course in, say, algorithm, basic algorithms? All of you have done a basic course in algorithms? Yeah. NP completeness?
Yes.
Okay, great. So, if you have seen NP completeness, then most of the time we have a very naturally we ask, if we are in graph algorithms, we say, hey, does there exist a set of vertices which satisfy certain property? Does there exist a set of edges of some particular size which satisfy certain properties, right? Now, this size, like, does there exist a path of length at least k in a graph that already quantifies that we are looking or we are seeking a path of length at least k? These are decision questions. Generally, these decision questions have in themselves some parameter hidden, right? Now, in polynomial time algorithm, what is the parameter? The most obvious parameter is the input size. And what is polynomial time algorithm trying to do is to obtain an algorithm which is polynomial in the input size. So input itself is a parameter there, right? But the dependence of my algorithm's running time is polynomial. But not for the problems which are not polynomial time, we do not expect, at least now, that we will be able to make an algorithm whose dependence will be polynomial time. So we start to look for algorithms which are brute force, but slightly better than brute force. Like, we are still trying to smartly search the solution space. Now, there are lots of approaches which have been used. Like, there is one whole algorithmic area where you actually take the input size itself as a measure, and you try to obtain an algorithm with as efficient as possible, although exponential, but in terms of the measure of the complexity or the measure of the running time is still, for example, Hamiltonian path, right? If I give you a graph on n vertices and I want to test whether they exist, or Hamiltonian cycle, does there exist a cycle, a simple cycle, which visits every vertex? Now, the most trivial algorithm is, if it has n vertices, we look for n factorial permutation, one by one, and check whether the adjacent vertices has an edges. And this gives you an algorithm with running time n factorial, right? But you can do smart dynamic programming, or you can do smart divide and conquer and get an algorithm with running time 2 power n and poly space. So compared to this n factorial, this 2 power n is much smaller number, although it is still exponential, right? And there is also a theory which tells you that you cannot have an algorithm for Hamiltonian cycle in running time 2 to the power little o of n unless some bad things happens. And so those are those aspects. Now, parameterized complexity is trying to see this algorithmic complexity not with that perspective. So the whole aspect or the whole emphasis here is that the input size we still want to be polynomial, right? But we want to associate some measure of complexity, and we want to design an algorithm with where the dependence on exponential could be limited to this function of this measure which I'm going to define, so that when this complexity, when this measure is constant, I still have polynomial, uniformly polynomial time algorithm, right? For example, what does it say? You have input size n, and you have some parameter k, which typically is solution size. We will see some examples. And what is the desire? You want to make an algorithm with running time f of k n to the power big O of 1. Now, let me just write it down this somewhere.
Second, use this one.
Okay.
This one is black.
Okay. And for our discussion today, let's make it NQ, right? Now, if for some problem, whatever that complexity is, suppose k equal to 1, what is the running time of this algorithm? It's polynomial. K equal to 10 to the power 10, which is still polynomial? It is still polynomial. I put this, it is still polynomial, right? So imagine that you are trying to design an algorithm. That's where the fun part comes. Like, where is an excitement? The excitement part is that you have to do something non-trivial, something very smart, to have an algorithm for an NP-hard problem. For example, let's have a starting example, k path, right? K path. I want to test whether a graph has a path of length at least k in the graph or not. What is the most obvious algorithm? First, we guess this k vertices and choose k, right? Now that we have guessed this k vertices, we want to check whether there exists a permutation such that the adjacent vertices, there's an edge. K factorial? This is an algorithm, right? Now, if I put k equal to 10, what is the running time of this algorithm? It's roughly n to the power 10, right? If I put 10 to the power 10 to the power 10, the running time of this algorithm is roughly this, right? Compare that algorithm with, suppose I'll make an algorithm for you whose running time is going to be k factorial into n. Suppose we are able to make such an algorithm, and we will make even faster algorithm than that. Now, what is the running time of this algorithm? For 10 to the power 10 to the power 10 is linear. Right? So you need to be smart to design an algorithm which does so much better than this, right? So what I'm trying to tell you is that for many of the problems which you will see, making an algorithm with running time n to the power some g of k will be very easy, or it might be very easy. But obtaining an algorithm versus this or this kind of algorithm is not easy. So in polynomial time, it's a battle between whether the problem has a polynomial time algorithm or not. In this world, it's again a function kind of battle, is that does this problem has this kind of algorithm, or does this problem has this kind of algorithm? Now the second question, when do we stop trying that the problem does not have polynomial time algorithm? What you do, that's okay, no more, I cannot try that this problem can be solved in polynomial. What do you do for that? You show that the problem is NP complete. Then you stop trying to prove that the problem has a polynomial time algorithm. So in this world, in this complexity also, there should be some theory which should tell, hey, this is the best we could hope for, right? So there is a theory which tells you which allows you to show, of course, the way P versus NP is based on certain assumption. Similarly, here we have certain assumptions which allows us to show that for certain problems, these kind of algorithms are optimal, right? So, so given a problem, there are two questions. First of all, is it this kind versus this kind, right? If it is this kind, then we need to show some appropriate hardness reduction. If it is this kind, we need to design an algorithm. Now, if it is this kind, is it this kind, or it is this kind, or it is this kind? I don't know. I mean, there are infinitely many functions. But asymptotically, what we try to show that, hey, we make such an algorithm and we give some reduction which will tell you that this is not possible, right? So for every question, there is always a notion of, is the algorithm which we have made is tight under certain complexity theory assumptions, right? So, I mean, this is the framework of parameterized complexity, is that we want to design an algorithm of this nature, and to be able to rule out we cannot have such an algorithm, or to be able to prove that such kind of algorithms wouldn't exist. So like there are thousands of possibilities, and we can make thousands and thousands of algorithms of this nature, and this area has flourished quite a lot in recent years, and a lot of new methods, new techniques have come across. Matroid, this is what I said, that Matroid is something which I chose to teach you, but we don't have to be fixed with that. I mean, we can learn on the way some other methods, some new things, and we'll see how it goes, okay? But the whole motive is that I want to design such an algorithm, and I would like to give you some methods for it, okay? So just a basic definition, for problems which you are able to make such an algorithm, they are called fixed parameter tractable, or FPT, anything. For our lecture, these are good algorithms and those are bad algorithms. This is good enough, whatever we call it. Okay. So this is what I have. Let's fix a couple of problems for the lecture, for a running example. So first problem is vertex cover. What is a vertex cover problem? You are given a graph, some number k, and what you want? You are looking for a subset in my vertices such that every edge has at least one of the endpoint in this set. Or you can also think of a vertex cover, a set of vertices which hits all the edges, or it's a hitting set. So if we take every edge as two tuple, right, two tuple, then it's basically a set of vertices which hits or which intersects every such tuples. Okay, that's what the vertex cover is, and the path is you're given a graph, and you're looking for a path of length at least k. And for the purpose of this talk, let's fix by path we will mean k vertices path rather than k edge path, because path is generally number of edges in this path. Now, are you okay with the definition of these two problems? Now read the definition. I mean, all of us understand the math symbol that exists for also. I don't need to explain it. Okay, so what is the complement of vertex cover? If a set of vertices is vertex cover, what is outside? So this is my vertex cover of a graph, and this is remaining. So this is my, what I'm going to call V prime, and this is V minus V prime. Can there be an edge here? No. This is called independent set. This is vertex cover. So always remember, all the edges are going across, either they are there or here. Okay? So this is like some simple definition, some simple path. Okay. Okay. Now that we are on definition, let me give you another definition. Okay, so let me tell you excitement. So I try to communicate my excitement number 1. Let's try to communicate excitement number 2. all of you write programs, right? And there are some times when you say, hey, if the instance looks like this, we can make some simplification. Don't worry about the definition, it's very formal definition. Okay, we make some simplification and we do this. Now imagine that you are writing a SAT formula. For example, you are writing a program for SAT and you see that some variable occurs only positively. What do? You say, okay, let it set it accordingly and simplify the instance. Or if some literal occurs negatively only, you do some simplification and do. Now there are many much more complicated pre-processing which you can do to an input. Now when an input is NP hard problem, what is success? When do you say that this pre-processing algorithm which I have applied is success or failure, or we have made some progress? How do we measure this? Like currently, like down the line 10 years back, these were like heuristics. So you see some structure in the input and you make them as rules. If I see this in my input, apply the following simplification, right? Now, but in classical setting, we need to have, let me use this board for you, or maybe I'll rub this, I don't need that much space there. Okay, so I'll just leave this for you. And I'll try to draw a box for you. Here's a box. I tell him, look boss, you're only allowed to take polynomial time. This is what it is mandated to do. It cannot, this black box or algorithm, it takes as input some I comma k. It returns some I prime k prime. Okay? So, and look, if this guy has to be nice, what does this polynomial time algorithm should do? It should not change my answer. If I gave him an yes instance to a problem, it should return me an yes instance to a problem. It should not change the answer. For example, I give him a graph which has a path of length k, and this returns me a graph which does not have a path of length k or path of length k prime. Then this is not a good algorithm. An algorithm is good, a polynomial time algorithm is good, or a pre-processing is good if it maintains the answer. Which in other words, in the scientifically, what it says that I comma k is a yes instance if and only if I prime k prime is a yes instance. And we have fixed some problem, pi or language, whatever you want to call. So with respect to this. So any pre-processing algorithm must maintain these two things. Given I comma k, it returns me an equivalent instance. Like yes goes to yes, no goes to no. Then only it is a nice, proper simplification or pre-processing algorithm. Now, two questions to ask. Suppose I'm trying to make such polynomial time algorithm for NP hard problem, and suppose I prime k prime has the following thing. Size of I prime is strictly less than size of I. Is it possible that we can make such a kind of polynomial time algorithm for a NP hard problem? This is NP complete or NP hard, whatever you want to call it. Complete, hard, whatever you want to say. Is it possible to make such a polynomial time algorithm that it takes an input and just reduces it by bit? Because then we can call it, this pre-processing algorithm is successful because, or this pre-processing algorithm is very nice because it takes an instance, applies some pre-processing algorithm and returns something which is smaller than what I gave it to him. Plus, it never changed the answer. Is it possible to make such an algorithm?
No.
Why?
Because we will come to trivial in a finite number of steps.
Exactly. So what he's saying is basically say, hey, if you make such an algorithm, to take this, feed it back to the same algorithm, and in finite many steps, we will be able to get some trivial instance for which we can try everything and find an answer. So obtaining such an algorithm in classical complexity seems hard, seems difficult, right? So what parameterized complexity tells is that, okay, no problem. Either this happens, or you are able to say that, look, instance has become small already, and we have to define what does this means by small already, that we cannot do anything, or I cannot do anything. And this whole kernelization algorithm tries to quantify what does that small means, that you are applying this step, and once somehow think like that, given an input, not every part of the input is hard or important for your problem. So in polynomial time, you are able to remove them, solve them, and you are able to come to a core of the problem, which is the which is the hard part of the problem, core of the problem, which is the hard part of the problem, and or the reason why the problem is NP hard, right? So this kernelization algorithm essentially tries to, define this part in a formal way. Let's see what it means. So what is this algorithm? It's an algorithm which takes an input, and how much time it takes? It takes polynomial in this, because it is not allowed to take more, and it has two things: x comma k is in L, if and only if x prime k prime is in L. So what it tells us that you gave me a language, you gave me an input, I return you an equivalent input, I haven't changed the answer, but it demands something more. He says, hey, your output instance should be upper bounded by the function of the parameter, right? Or the function of the parameter. Like for example, in the k path, if I give him an input of a graph G and a number k, and I'm asking for a path of length k, it should return me a smaller instance. Either it can tell me that, okay, well, it should return me an equivalent instance where the size of the instance is bounded by f of k. So basically what I'm saying is that this is an algorithm which either returns this or comes back to us and says, hey, this is bounded by some function of k. This is what. So by giving this a slightly more power, I have made a bit more meaningful question, right? So in polynomial time, either it is able to reduce in a classical sense, or we are able to deduce the size of the reduced object is small, and by small we mean function of the parameter, right? And we say that the problem admits a polynomial kernel if this function is polynomial in k, right? Is the definition clear to all of you? If something is not clear, I think this is a good time to ask questions, because these are the two basic definitions which we need to carry along with us. So you can take a minute, gather the definition.
So this definition is only used when key is not less than the input size, right?
If k is not less than the input size.
Yes, I mean, since the kernel algorithm gives us both input and
output
new parameter,
yes,
limited by
function of k,
by the same function, so essentially key is always tightly related to the input size.
It is generally so in parameterized algorithms. Okay, this is a very good question which I thought I will avoid answering, but okay, since you have brought it up, okay. So this parameter k is encoded in unary.
Pardon?
The parameter k is encoded in unary. It is not encoded in binary. Right? So, and this is why. So when you start encoding in binary, even though you have a like you could, like this and this could be tied in a very unrelated manner. You see what I'm saying? But generally what happens is that this parameter is smaller than your input, right? It is generally smaller, but there are problems where this could become a bit difficult to handle, like subset sum, because you have n numbers. But input has each number is like logarithmically you can. So, but what you could ask is that the total sum could be much larger, still with polynomially many bits, right? So it makes little bit life harder. So we demand that this k is encoded in unary, right? Like we write like this. So that, I mean, it is physically k, like k bits. It's not log k bits, it's k bits. Okay, so that is a kind of not very, I don't think it's a very good definition, but somehow that is to make things meaningful. This is, so you're right, somehow it is tied down. In general it is smaller. Look at k path. For example, for now let's just fix ourselves to two very small examples, k path and k vertex cover. They are definitely much smaller than the input size, or they are upper bounded by the input size, right? So even if we return p of mod x and forgot that k, things should have made sense, polynomial input size. But for parameterized problem, we do not think x as input size. So whenever someone tells you what is an input size for a parameterized problem, it is not this alone. Input size, according to is mod I. This is encoded in binary. This is why let's use this plus k. This is a real input size. But let's not worry for now, because it is primarily useful. And when you start doing complexity theory, you need to be careful. If you start showing lower bounds on these things, you need to see in which language you are talking. But for algorithm in general, this is what it is. This is what our input size is. I hope that answered your questions. Little bit, maybe not completely, but. So let me give you an example of kernel. Like very simple example. If a graph has an isolated vertex, a vertex where no edges are incident, are they useful for your purpose? You can remove them because they are not going to participate into, or you can obtain a vertex cover without these vertices. So it's a simple example. Here is another example, another reduction rule. If I have a vertex V whose degree is k plus 1, at least k plus or maybe more, then what happens if you decide not to pick this vertex in your vertex cover? What was the definition of vertex cover? It should at least pick one endpoint of every edge. So if you decide not to pick this red vertex, you have to pick all the green vertices. Now if the neighborhood of this vertex is more than k plus 1, then, and if you are looking for a vertex cover of size k, right, it cannot be possible if you decide not to pick this vertex. So what is our reduction rule? I say delete this vertex from the graph and drop the parameter by 1, right? So I delete this vertex in the graph and I say, hey, in the current graph, does it have a vertex cover of size k minus 1 or not? Okay? So we apply these rules until no longer possible. Now, what conclusions can we draw? Outcome 1, if G is not empty and k drops to 0, then answer is no. I apply these two reduction rules, right? I apply these reduction rules and k drops to 0, graph still has an edge. It means that the answer is no. Now why? Because these reduction rules are safe. What I mean by safe? So what you need to show to be safe is the following. This. So in this language we have to show G comma k is a yes instance if and only if G minus V comma k minus 1 is a yes instance. Meaning if you give me a vertex cover of size k here, I can get a vertex cover of size k minus 1 for this graph. If you give me a k minus 1 vertex cover of this, I will be able to get a vertex cover of k here. And that's clear. If you give me a vertex cover of size k minus 1, I can obtain a vertex cover of G by adding V to my vertex cover and get a vertex cover of size k. Now, you start with a vertex cover of size k here. If it has a vertex cover of size k, it must include this high degree vertex. It means if after I delete that vertex, that still remains a vertex cover of G minus V. And since we have deleted this vertex V, the parameter drops by 1. So you have to prove this. Basically what we are saying that if you started with yes, the small instance is also yes. So you keep applying this, and by transitivity, if my graph still remains and k is 0, if I give you a graph G which has edge and I ask you, does it have a vertex cover of 0? What should you say? No. So that's an easy answer. You reply back. This is what it means. If G is not empty and k drops to 0, then you return no, because after one application of this rule, my k has dropped by 1. So it is possible that I'm able to apply this reduction rule more than k times. So my k has dropped to 0, but my graph does not have, graph has still an edge. Now, okay, so what is an observation? Do you agree? We stopped in middle. Why are we not able to apply these rules? A, there are no isolated vertex, and every vertex has degree how much? At most k. K or less. Agreed? So what can we say at this point of time? If the graph has strictly more than k square edges, can we say no? See, this is my vertex cover, which is supposed to be of size at most k. Each of them, how many edges are incident? At most k, because degree is bounded by k. So if at all there is a vertex cover of size at most k, and the number of edges, so number of edges they can cover is k into k, which is like k square. So if the number of edges is more than k square, answer is no. It's like you do a simple counting. It's like, okay, k guys, each can take care of k edges. So the number of edges is more than k square. We say no, right? And that's completely correct output. So this is what this box is. So I am just making a box here for L being vertex cover. Okay. Now, so how many vertices can be there? If the number of edges is bounded by k square, how many vertices is there in that graph? 2 times k square at most, right? I mean, we can do something more clever, smart, but number of vertices is bounded by 2k square is correct, right? Because an edge has 2 endpoints, the total number of vertices is at most 2k square. So, what is an outcome of this polynomial time algorithm? Either we are able to tell you completely solve the problem by returning yes or no, or we are able to return an equivalent instance whose size is bounded by k square, right? So for vertex cover, we are able to bound the number of vertices by 2k square vertices and k square edges. Okay guys, now tell me, so for vertex cover, I want an algorithm with running time which looks like something like this. Can you make an algorithm with running time which looks like this? If I'm looking for a vertex cover of size k, n choose k is an algorithm. Agreed? I try all possible subset of size k, check whether it is a vertex cover or not. How do I check? I check whether for every edge there is a vertex. I'm not happy with that algorithm. No. I want an algorithm whose running time is f of k dot n to the power big of 1. Take your time, take your 2 minutes. I'm not in a hurry. Does this algorithm runs in polynomial time? Like coming up with this, does it run in polynomial time?
Yes.
You remove an isolated vertex, some polynomial time, I don't care, some polynomial time. Let's call it n to the power 50. I'm sure it runs, I think n cube is best. You can make it run in linear time, but let's call it n cube. Okay, guys. So you told me that answer doesn't change, right? Now, what should I do for this problem? Let's rub this. Okay. Now, I gave you a graph g comma k. You first apply this kernelization algorithm, right? You get an instance g prime k prime where k prime is less than equal to k, because if you remember, we were only deleting, we were decreasing the parameter. And what was an answer? G has a vertex cover of size at most k if and only if G prime has a vertex cover of size at most k prime. Agreed? Now let's apply our trivial algorithm, right? I want to find a vertex cover of size k prime here. How much time will it take? It will take this is my trivial algorithm, right? Size of vertex this, choose k, and testing whether it forms a vertex cover or not. Vg prime plus Eg prime. In linear time, we can test whether a particular vertex cover is by look at your edge, just check whether it is there. Maybe some factor of k. So let's put down how many vertices are there in G prime? Huh?
2k squared.
2k prime square actually. Important. 2k prime square. What is, sorry, k prime into k, some polynomial, plus running time to come from here to here. Some polynomial. Okay? What is the nature of this function? Is it like this, or is it like this? This function looks like this or looks like this?
The latter.
Huh?
The latter one.
What?
Lower.
Lower one, right? So, hey, this algorithm is basically some f of k prime is less than or equal to k, blah blah blah. In fact, this is an algorithm whose running time is k log k, to the power big O of k log k, right? Because it is like k prime to the power k prime, which is like 2 power k prime log k prime. So this is a form of the running time. So we know how to make an algorithm, right? So now if Piotr tells you to make kernel, so you can make kernel like this and get a faster algorithm. Okay, but that was not the point. So basically, look, I did nothing. All I did is say, hey, my input was big. I have made an equivalent input whose size is a function of the parameter. Now, any brute force algorithm on this equivalent small instance is a fixed parameter tractable algorithm. Any algorithm which you can think of make for any problem, 2 power any input size, if the input size itself is a function of the parameter, then this a bad algorithm is also a fixed parameter tractable algorithm, right? So that is a key point here. But there are much faster algorithms for this problem. This is a very bad algorithm, okay? And since this is not a course on kernelization, you can do more smart stuff, like literally more smart stuff, and you can design a kernelization algorithm where I didn't give you a good algorithm. You can design an algorithm where you can prove that Vg prime is less than or equal to 2k prime. Okay? And Eg prime is still k prime square with these two parameters, right? Now, size-wise, if you take the total size of the kernel, nothing has changed, right? I mean, in terms of order, this is an order k square kernel. This is also order k square kernel. But we can prove some extra property of this output instance is the number of vertices bounded by 2k prime. Now, what is the running time of that algorithm then? 2k prime, choose k prime, 4k prime, right? This you can prove. 2k prime, choose k prime is less than or equal to 4k prime, because this is 2 to the power 2k prime. I mean, it's much smaller. N choose n by 2 is definitely less than summation I equal to 0 to n choose I, binomial theorem, which is 2 power n. Nothing more, no magic, please. Okay, so this is it. And the cool thing, let me tell you the reason why I told you, hey, you can make it, but if you think in terms of size, like size, right? Now the question is it possible to obtain a kernel for vertex cover with the following size, right? So currently, even in this, the size is dominated by k prime square. Is it possible to get a kernel for vertex cover where Vz prime plus Ez prime is, say, sum 2 minus epsilon, big O of k to the power 2 minus epsilon, any epsilon, like think of this as 1.9999. Is it possible to obtain a kernel for vertex cover where the size of vertices plus size of edges is order k to the power 1.9999, as many 9 as you want to put? Is it possible? Answer is no. Unless, if you people know classical complexity, the poor polynomial time hierarchy will collapse to some second level. Or maybe, and in my own language, when Earth will hit the sun, then everything will be anyway bad. So till then we are safe. Okay? So you can prove these kind of things. So this algorithm, this kernel algorithm, which looked trivial, it's like, yeah, you know. So it seems it is optimal, and you need a big machinery to prove why these kind of things are not possible unless some unlikely collapses happens in complexity theory. Okay? So that is my excitement number 2. So simple, but still very powerful. And there's a whole question, right? There's a whole world of questions there, and still a very, very active area. I give you a problem. First of all, first question is this problem like this? Right? That's of question number 1. Now the question number 2 which we ask, okay, if it is like this, does it has a polynomial kernel like this? Polynomial. Here the size of the output was f of k, right? We will see an algorithm for k path with running time something like some c power k. We'll see an algorithm for k path, but for k path we can prove that you cannot have any such algorithm where the output is bounded by anything polynomial. You see, even if I'm asking you a kernel of k power 100, not possible. K power 500, not possible. And in fact, you can prove slightly super exponential lower bounds for these kind of problems. So there are lots of questions still unanswered. I mean, there are a variety of questions unanswered. The tool which I was trying to tell you, this Matroids and all this, which is one of the goal to explain you, has helped us resolve some questions about some problems, whether they have a polynomial kernel or not. But there are still many fundamental problems, basic problems, for which we still do not know the parameterized complexity, like kernelization complexity of them. For example, do they have kernel of this nature or do they have kernel of this nature? We do not know. So this is still very active area. Lots of papers are being written. I mean, all kind of questions are there. Particular problem, class of problem, classical, like introducing new methods, new ideas, and things like that. Okay? Okay. Okay. Okay, so now there are two ways forward. Either I can tell you an algorithm for iterative compression and odd cycle transversal. If you have people seen iterative compression?
Well,
Some of you. Many of you have not. Okay. So the reason why it appeared here is that because it's a very, for this problem, first of all, even obtaining a fixed parameter tractable algorithm was a big question. It remained open for a long, long time before we started to understand this problem. And then whether it has a kernel of this form or not was open roughly for 10 years. And finally, we realized that, oh, it's nothing but a matroid. But this aha moment came 10 years later. So this is why this problem was interesting. And okay, so I think it would be much wiser for, if you have not seen parameterized algorithms, to see one or two more non-trivial parameterized algorithms, and then we will come back to matroids and try to connect these examples in a rightful way. Okay? Okay, so I taught you how to make that kind of algorithm by doing this polynomial time preprocessing. Okay? But before I teach you iterative compression, I'll teach you in a minute. Let me make an algorithm for vertex cover using branching. Here is my picture. What does it tell you? So I don't have slides for vertex cover because I was not hoping to make one for you. Okay guys, 4 power k prime, an algorithm for vertex cover. If I do all this big machinery, but let's see some simple, obvious, trivial algorithm. I will not rub this picture for you. Don't worry. Okay. And it's very important to know the history. Okay. So let's. So whether it has this kind of algorithm or this kind of algorithm, like people didn't know till 88, 89, okay? Till 88, 87, 88. And I don't know how many of you heard of this graph minors and blah blah of Robertson and Seymour. So there is a way to make an algorithm using graph minors, which shows, this is what Mike Fellows, Downey and Fellows showed, that, oh, this problem has an algorithm, running time f of k n cube for vertex cover in 88, 89. But no one could see this algorithm. What I mean by no one could see this algorithm is for every fixed k, there's a different algorithm. Like if you put k equal to 3, it's a different algorithm. K equal to 4, it's a different algorithm. For example, the way in circuit complexity, for every n, we make different circuits, right? Similarly, so those are non-constructive tools. So similarly, in parameterized algorithms also, we do have non-constructive tools. And so what it happened, so basically it said that this algorithm did is said, okay, if you are looking for a vertex cover of size k, then I will make an algorithm which basically said that, look, if a graph does not have vertex cover of size 5, then following kind of graphs cannot exist in your graph. Now, what are these following kind of graphs? No one could see. No one knew. No one knows. Okay? So they are completely non-constructive. So basically what it says that, well, I can take an algorithm, in which it's hardwired, which kind of graphs cannot exist, which only depends on 5, so it's only constantly many. And graph minors tells you that these kind of graphs can be tested in polynomial time, in n cube time. So your algorithm is hardwired with this class. You give him input, he checks whether these graphs are there or not. If it is not there, it says yes, it is a yes instance. If it is there, then it says no, it's not a no instance. So this was the algorithm which we made in 88, 89, and that was a big result. So if you go to Fortnow's web blog, he was trying to tell 10 results which he found surprising in thesis was, it also includes this algorithm. Okay, so it's quite nice. Okay, so no one knew. So then the kernel which I told you, there was a guy called Jonathan, I think Sam Buss. He was doing something in complexity and he came up with this kernelization, and then algorithm with k power 2k was made, the algorithm which I just now told you. Okay, and then 1994, Papadimitriou and Yanakakis were trying to understand the miniature version of the problem. What I mean by miniature version of the problem? He said, well, is it possible to test whether a graph has a vertex cover of size log n or not in polynomial time? What I'm asking for, does this graph has a vertex cover of size log n or not in polynomial time? Now, trivial algorithm would take n to the power log n, because n choose log n. So what they did, so now if one way to prove that you have a log n size vertex cover or not in polynomial time is, if you give me an algorithm which is like c power k, some polynomial n to the power big O of 1 for some fixed constant c, then if you substitute k equal to log n, this is polynomial time, right? So they came up with an algorithm with running time 3 power k into n. Papadimitriou and Yanakakis, they came up with this algorithm to show that the vertex cover has, like log n vertex cover is in polynomial time, because 3 power log n is polynomial. But they couldn't do this for k path. So for k path, people knew this k factorial algorithm, but people did not know. So there was an algorithm in those days for k path with running time order k factorial dot n. But that cannot solve your log n vertex cover question, because it is 2 power k log k times n. If you put k equal to log n, this is not polynomial. So they left open, is it possible to get such kind of algorithm for k path? Is it possible to get such kind of algorithm for k path? And it was open for 3-4 years before Allen, Eustert and Zwick came up with this idea of color coding, which is like one of the most easiest, simplest approach, but with a lots of powerful impact to show that k log n, checking whether a graph contains a path of length at least log n or not, is in polynomial time. Okay, so now that we are on the log n path, because it's very important, let me mention, if a path contains, so there are 3 questions. So they were able to answer, does this graph contains path of length exactly equal to log n? Very nice. Or directed graph contains a path of length exactly equal to log n. But they were also able to answer, does this graph contains path of length at least log n? Because hey, if I'm able to check whether a graph contains path of length log n, it's because if a graph has a path of length at least log n, it also has path of length log n. What about cycles? If I tell you graph may contain a cycle of length log n, but it may not contain a cycle of length at least log n. You see what I'm saying? Right? So they pose this question, and there's a very clever trick in undirected graph to prove that graph contains, to get an algorithm for checking whether a graph contains a cycle of length at least k in undirected graph. Like there's a very clever trick to get these kind of algorithm for this problem. And for the directed graph, this problem remained open. 1 stock, 2 sodas, people wrote papers on this in directed graph, like lots of papers, till 2004. And we still couldn't, at least for directed graphs, we couldn't get an algorithm of this time to test whether a graph contains a cycle of length at least log n or not, because for that you need such an algorithm. And using Matroides tricks, which I'll teach you, you can actually do it. So finally in 2014 we settled this problem. That was our main motivation. So I mean, these are very little and basic questions, but still some of them we do not understand. Okay, so this is an algorithm was made. And then I was looking at a textbook by Kurt Melhorn. He has written algorithm design 1, 2 and 3. Okay, there he has he gave as an exercise 2 power k dot, an algorithm for this problem. It's an exercise in his book, and it is from 82, 83. We didn't know. I mean, who thought that in the homework exercise? And there's another homework exercise, I must admit, in that book, which I didn't know, and I wrote not 1, 2 papers on that, like solving that homework exercise. Like, and in good journals, like Transactions and Algorithm is a good journal, but all I did was actually solving that homework exercise. I mean, so this can happen, okay? So I only saw this in 2007 or 2008, these homework exercises, and then I was a bit embarrassed that even in those days people knew how to solve it. That he doesn't even put it, teaches it. He actually has put an exercise without hint. So you can imagine. Anyway, so coming to this algorithm for vertex cover, here's an algorithm. What do you think? It's a very obvious algorithm, but somehow most simplest ideas doesn't come very naturally. Look, if you have an edge, u and v, what are you looking for? You're asking, does there exist a vertex cover of size k? Now, any vertex cover of size k by definition should either contain this vertex or contain this vertex. So you make a search tree. In one branch, you say, hey, does there exist a vertex cover of size k minus 1? If I decide to pick u in my vertex cover, if recursively this returns me yes, yes, or I ask, suppose I decide to pick v into my solution, does g minus v contains a vertex cover of size k minus 1? If this branch returns me yes, it has a vertex cover of size k minus 1, then I put correspondingly v or u, and I return to your vertex cover of size k. If both these branches return no, I say no, because any vertex cover of size k must contain either u or v. So what is the running time of this algorithm? Let's write down the recurrence. T of k is less than or equal to 2 times k minus 1. Of course, some polynomial, but let's count the number of. And how much is this recurrence? 2000. This is an algorithm. Very smart algorithm, no? But if you look at this history, please go and look at the people whom we all say, yes, great, they are the greatest scientists we have ever known. I mean, even big people miss the basic idea. That's all that I'm trying to tell you.
Question. How did you choose this particular edge?
I picked any edge, because from any edge, my vertex cover has to pick one of the guy. So you just pick some edge. This is the whole point, right? You pick some edge and do this. Nothing special about it. Okay.
Can it be the case that Papa Dimitri and Yanakakis just were not trying to improve this running time?
They give much more complicated 3 power k algorithm. They say, okay, let's consider maximal matching in the graph. If the maximal matching is more than k, answer is no. Now look at this maximal matching. Vertex cover could intersect like this, if it intersects this way, then this reduces to bipartite vertex cover, and this is the algorithm, right? I mean, I'm not saying it's wrong, I'm just saying that they just found that natural, but there are even more natural and basic idea which people just missed over the years. And they needed this algorithm to show that logarithmic vertex cover is polytype. That is what their motivation was. Okay, now we move to slightly harder problem, slightly harder concept to digest, but if you bear with me, you will be able to understand. Okay, so welcome to part 1, part 2. And another second thing, please feel free to ask questions. Let language be not the barrier. I am also not a native English speaker. Every paper I write, at least 2 reviewers out of 3 complain that English is extremely poor. So it's okay, it's not our native language, so we shouldn't worry about that too much. Anyway, so let me teach you what is called iterative compression and odd cycle transversal. Now, it is very surprising small but very powerful tree. So generally this trick or this idea has been useful in minimization problem, like at most k vertices which does something. Now, just now you noticed we were trying to make an algorithm for vertex cover. We said, hey, let's pick an edge. This is an object which I need to hit. So let's branch. Now, in odd cycle transversal or graph bipartization, you are given a graph G, integer k, and your objective is to delete k vertices to make graph bipartite, right? So I want to delete k vertex so the graph becomes bipartite. What was this vertex cover problem? Delete k vertices so the graph becomes independent. It does not have any edge. In odd cycle transversal, what is our objective? We want to delete k vertices such that graph does not have any odd cycle or graph becomes bipartite. Agreed? Because a graph is bipartite if and only if it is two colorable or if and only if it does not have odd cycle. Agreed? Now, one trivial approach would be that, okay, our objective is to forbid or to delete all odd cycles. Let's find an odd cycle and branch on them. No? Is it like the way I did for the vertex, we did for the vertex cover? What are we trying to do here? If you notice, this strategy is nothing about vertex cover. Any problem where here we could say this odd cycle cannot exist. And how will it not exist? If one of these vertices will go to my solution. So I could say, okay, u1, u2, u3, dot, 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 ul, g minus u1, k minus 1, g minus u2, k minus 1, ul, k minus 1. Now, what will the recurrence here? I mean, if I find a length L cycle, then this is L. Now, the only problem was that for a vertex cover, we had a bound on our forbidden structure. In odd cycle, it could be a cycle of length root n or maybe n by 2. So this algorithm could well be like this. And hence this strategy is not a good strategy. Agreed? I mean, why we cannot do this is exactly this. So whenever you are able to, so what does this tells us? Whenever we are looking into a problem, parameterized problem, where we are able to find a small set of vertices, a small set of objects which must go into the solution, we can apply this branching strategy. But when we are not able to do it, either we do some clever pre-processing or clever way of finding these small objects which we must destroy, we must hit, or we move to some different strategy. Okay? Now, here odd cycles we do not have bound. We know that we need to hit all odd cycles, but odd cycles could be of different length, and that is not in our control. And that is why just normal branching strategy does not work. It's 2014, we have come to know 2013 that odd cycle transversal problem is nothing but a vertex cover problem. But I don't have time to tell you that. But the algorithm which you did just now, what did you did? Find a edge, branch. This is also works for, this is exact algorithm, nothing. If you do this, it is also an algorithm for odd cycle transversal. No? You don't believe it? So here's my algorithm for odd cycle transversal. Pick an edge, branch. It's an algorithm for odd cycle transversal. It's the truth.
Really?
Yes.
Well, at least it is not straightforward.
It's absolutely not straightforward, but this is a correct algorithm. You have to just check whether it's an odd cycle or not. That's all. Like graph is bipartite or not. That's all that you need to do, more or less. Of course, I'm hiding a lot of things, but this is an algorithm.
So you mean at any step we can take any
Edge, branch. This is it.
Just any.
Any edge. Okay. But I need to teach you technique, right? So if you're really curious, interesting, I can spend my half an hour sometime, today, tomorrow, anytime. If you're really curious that why for this problem it works out.
So When it was proved, discovered?
It was discovered like here and there, but we only managed to get this algorithm in 2011, 2012. So the fastest known algorithm for odd cycle transversal is this. This runs in time 2.32 to the power k. Is this the algorithm? Okay, here is in the bullet form. This is an odd cycle transversal. Graph, integer, we delete, graph becomes bipartite. Everyone knows what is bipartite graph? Yes or no? Yes. Yes. Good. Okay. So let's try to do some polynomial time algorithm. So you are given a bipartite graph G, what I call annotated problem for bipartite graph. So what are you given? You are given a bipartite graph, two sets B and W, maybe, is it overloaded sentence? So let's draw a picture. Whenever things are overloaded, I also have a picture, I guess, in the next slide. Okay, so this is the problem which I want to solve. Forget about odd cycle transversal problem, but this is the problem I want to solve. You are given a bipartite graph G, two sets B and W, and an integer k. And what you want to do, find a set S of at most k vertices. You want to find set of S at most k vertices, so that if you delete them from the graph, okay, remaining black and white, remaining vertices which are black, I'm able to color my graph with black and white, so that remaining black vertices go into the black side, and remaining white vertices become white. So essentially how it looks like is that, let's ask ourselves a question. So this is my bipartite graph. Okay, some set is called black, like some are here, some are here. Right? Now our idea is that I want to delete k vertex from the graph, okay? Delete k vertices from the graph. And what do I want to achieve? Some set S, so that you have another two coloring where remaining black vertices are here, and similarly white vertices are here. So do you understand the problem? Okay, I give you a graph, bipartite graph. I give you two sets, black and white, and I say, can I delete small number of vertex so that I can come up with another coloring that the remaining guy becomes black, so which are in conflict? These white guys are in conflict, right? Basically what I'm saying that these people, white, should have been moved to this side, this black guy should move to this side, right? This is essentially, and on the way to moving these things, if some vertices needs to be deleted. That's a goal. And we want to make a polynomial time algorithm for this. No, like classical polytime algorithm for this. Is the question clear? Okay. So what I say, find an arbitrary two coloring B0, W0 of G. So this is your B0, W0. Graph is bipartite, such a coloring exists, right? Now it is clear. Now we have some black vertices, we have some white vertices. And what is our objective? If we want to delete small number of vertices so that blacks can be merged into one side and whites can be merged into one side, and the graph still remains bipartite. Or think of this way, you want to find another partition of this. You want to find another partition of this so that number of vertices which you need to, like I want to find this partition so that the number of vertices which are in conflict is small. And what I mean by conflict, black guy should have been come here, but it remains this side. W should have gone there, but it remains this side. So you are looking for a conflict, or you are looking for another coloring of this graph where the number of people which are in conflict is minimized, right? So basically, if they are less than or equal to k, you delete them. You have your desired coloring, right? So what are we looking for? You are given a coloring. I fixed a coloring for you. I'm saying come up with another coloring where the number of people which are in conflict, and by conflict, a black guy should have been moved to the black guy, but has not moved. White guy should have moved to the white side, has not moved, is minimized. Okay? Okay. So this is why I call which vertices are in conflict given this. This vertex is in conflict, this vertex is, like currently these are in conflict, right? We want to go to another coloring where conflict is minimized. But which people are in conflict? These guys should move to this side, this guy should move to this side, and that is why they are in conflict. So basically what I'm saying, what is the goal of these two vertices? Either they should change their color or should be deleted. This conflict vertices, either they should change their color or be deleted. And what can we say about this vertices? Are these vertices in conflict? No. So they should just maintain their color. Are these vertices in conflict? No. They should remain the color. Now we have to find a condition which says blah 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 may exist if and only blah 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 things will happen. Okay, and here it is. Okay, what is it saying? That look, if you are looking for a two coloring, so I say remain, be whatever you are, you remain conflict, remain conflict. Okay, essentially what I'm saying to you is that if you are looking for such a nice object, then the set of vertices which you are going to remove, some S which you are going to remove, should have the following property. Now look at this side, whichever is remaining, guys. Is there a path from conflict to remaining? Look, it's a bipartite graph, right? It's a bipartite graph. So now look at this conflict vertex, this remaining vertex. Can there be a path from a conflict vertex to remaining vertex? Well, if there is a path, or it's like this, any path will go like this and finally come here. Now if these two vertices, can this path exist in my hair? Look, suppose such path exists, right? Such path exists. Now, I start from remaining. Where will this vertex go? Its neighbor. It should go to the other side. Now, where will this vertex will go? It will come to this side. So basically, the length of this path is odd. A path between R and C is odd. Right? So if this path remains, and suppose this guy has been colored black, what will this guy be colored? White. Then where will its neighbor be colored? Black. Where this guy will be colored? White. Where will this guy be colored? Black. But then these two guys are in conflict, right? So if you are trying to minimize minimize from C, you are trying to minimize what? You are trying to find another coloring where the number of vertices which are in conflict, which I call S, right, basically should kill all the paths from R to C, any. So this is when R to C is this path. What about paths from R to C, which is like, should this path remain? Let's ask ourselves a question. Should this path remain? A vertex here X and a vertex here, call it Y. Okay? Suppose this path exists. Let's ask ourselves a question. Basically means that suppose this has been got black. What will this guy get? White. What will this guy get? Black. What will this guy get? White. What will this guy get? Black. And this white. Hey, but all your objective was to make these guys black, right? So if such a path will exist, so I'm just trying to tell you that whatever kind of coloring we want, there are some necessary condition that whatever that set S we are trying to delete such that we have a desired coloring, that should definitely destroy certain kind of paths. And what are those paths I'm trying to characterize? I'm saying look at your conflict vertices, look at your remaining vertices. There cannot be any path from remaining to conflict vertices. And I give you example why. Because if such kind of R to C path exists, then we have a conflict between black and black, but they needed to be black and white. Here I wanted them to be black and black, but they have a conflict because if this path remains, you will have black to white path, right? So it is very clear that whatever that set S which we are trying to remove, such that remaining black guys can go to one side, remaining white guys can go to this side, then such paths cannot exist. Okay, this is my motivation. Okay, so the problem is that you are given a bipartition, some black set, some white set. I want to delete some vertex and come to another bipartition such that the remaining black guys are in one side, remaining white guys are in the other side. That's a goal. And what I'm saying that G minus S, that set S, has required two coloring if and only if S separates C and R. That is, no component of G minus S contains vertices from both C minus S and R minus S. You cannot. So every component after I delete this S, look at any connected component. It either contains vertices from remaining or it contains vertices from change. We will prove this formally, but I just want you to observe the statement. And my motivation is exactly those two lines, that why I want such kind of things. Okay, let's prove the forward direction. In a two coloring of G minus S, each vertex either remained the same color or changed color, right? What I'm saying, look at the forward direction. What we are trying to prove, suppose I found some S such that no component of G minus S has both change or both remaining, right? So how does it look like after this? So here is an S, we deleted. Now we have some connected components. It contains some vertex or it contains some change vertex. If it contains vertices from change, it only contains vertices from change. If it contains vertices from R, it only contains vertices from R, but it doesn't contain both, right? This is all that I'm saying. Then I'm saying that there exists bipartition like this. Isn't the forward direction obvious? Look, graph is still bipartite, no? Okay, I don't know which side is easier to show.
It's quite obvious, so maybe we can.
Is it obvious to all of you? Okay, I'm not going to skip, don't worry. Okay. Okay. So first is, what are we saying? In a 2 coloring of G minus S, which, look at this. This we already proved. Look at this 2 coloring of G minus S, right? Now, what did we say? If you are looking for that set S, it cannot contain paths of this nature or contain paths of this nature, right? It means if we have deleted S, the vertices of R and C cannot be in the same connected component, because there is no paths from the vertices in R to vertices in C. Like, is it possible to get a 2 coloring? This is what I'm saying. Is it possible to get a 2 coloring like this? I told you this is a necessary condition. If such a path exists, such a coloring cannot exist. Right? So the first direction is exactly trying to formalize this. Basically what it says, that if this is your G minus S, it has a desired coloring, but if it has a desired coloring, you cannot have path from remaining to change. Because if I had a remaining to change a path, then we cannot have this coloring, because I start from the remaining, change, remaining, change, remaining, change, and I will get a conflict path. So this is not possible. This is all that. So whatever I was trying to make this intuition, forward direction is just making that. This is why I say it's a necessary condition, that if you are looking for such kind of coloring, then it is necessary for us to destroy these paths. And if I started with an S which destroys, which basically gives us this coloring, then we have definitely killed these paths. Now, the reverse direction is what, according to me, is obvious, but is quite interesting, is that look at a component. Each component contains either change vertices or the remaining vertices, right? Each component either contains change vertices or remaining vertices. What is the property of change vertices? They need to change the color, right? So you find some partition, and if these guys, some of them needed to be black, some of them needed to be white, just change the coloring to match with the remaining guys. That's it. So what I'm saying is that, look at after deleting this, either it contains a change vertices or remaining vertices for the backward direction. Okay. What is the meaning of remaining vertices? So look at the current partition of them, right? So when you look at the induced partition here, what do you know? That these guys needed to be remain like this. Fair enough. And what do you know about this? If I look at the current partition of these people, these guys need to change their color, these guys need to change this color. But it is bipartite. So you flip the coloring. If you are calling them, before you were calling them B0, W0, now you call them W0 prime, B0 prime. It's a valid bipartite coloring because they are connected component, right? So what I'm saying, that you go through each connected component, look at their induced partition here. If it is remain, guys, you don't change. If it is change, you just change. Everyone will change its color. This is it. And we have got such a coloring, right? So after you delete this S, go through each connected component, change, just look at the current partition, just name them differently. That's it. Like, does it matter if I call it B0 W0 or call it W0 B0? I mean, it doesn't matter if they remain the connected component. But what we have able to achieve, that we are able to find a coloring of this part such that you have nice properties. Okay? So how much time do you need to find this? Isn't this min cut? Max flow, min cut, does it? Right? So basically all that I did, even if I didn't do a very good job, all I try to do is that whatever problem I gave you, I try to recast that as a min cut problem. And I can solve min cut, even if you don't know, in this much running time. We can check if there's a S that separates C and R in K times this, because basically you need to do K round of max flow min cut iteration. That's it. So if you do not know, it's okay. This can be done in polynomial time using max flow min cut. Okay? Okay. So we can do this problem in polynomial time, but that was not our goal. We were trying to solve some odd cycle transversal problem, blah, 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 blah. Okay. So in iterative compression, this is what you will be given. What will be given? We are given two things. You are given a graph G, integer k, and a set Q of k plus 1 vertices so that G minus Q is bipartite. So what are you given? So this is why it is amazing, is that you are given what are you given to you? You are given G, a set Q, and what is the property? G minus Q is bipartite. Don't ask me who gives you this. Okay? We will see. It's for free. Okay? That's the point. But for now, suppose I gave you. So basically what you are asking, this is why the word comes compression. So you are given a problem and a solution, and you are looking for a solution which is smaller than this, right? This is why the word comes compression. And we will see in a minute why it is called iterative compression, but for now let's see why it is called compression. So this is why it is given. Now what we have to do? All we know is how to solve that bipartite annotation problem. So let's reduce our problem to that bipartite annotation problem. So this is our Q. So we branch into 3 power k plus 1 cases. We say, hey, some of these vertices, after I delete the solution, which I don't know, but either it is part of the k size solution we are looking for, delete it, and these vertices are not going to be part of k size solution. But if they are not going to be in the k size solution, how are they going to be partitioned? You see what I'm saying? So basically what it says is that look at your Q. This is bipartite Q. We know, and what are we looking for? I'm asking question, does there exist a k size solution? I said okay. Suppose my S is the solution, the superstar. Okay, now this S, how does it behave? It might pick some people of Q. I mean, he's allowed to pick. So this is what I meant deleted, the red vertices, that these guys could go to your solution. So we will guess that. Now remaining guys are not going to be deleted. It means they will be part of the bipartite graph which will be remaining after delete my S, because S could be here, somewhere here, and somewhere here. Now if these guys are not going to be deleted, then they will be partitioned into 2 parts. I don't know which the part is, but let's guess. Some black part, some white part. So how many such partitions are there? 3 power k plus 1. So we try all. The way we were branching an edge, either this or that, I said, okay, let's branch into many ways. 3 power k plus 1 ways, which basically tells you guessing which vertex from Q goes into the solution and the remaining vertices in which way they are partitioned. Of course, some guess could be wrong, because maybe you partition this into 2 parts like this and there's an edge here. This is not a valid partition. Then you just forget those. You do not go further, right? So this is what I meant. Trivial check, no edge between 2 black vertices or 2 white vertices. Otherwise, that's not a valid guess. Now, what should we do? Okay, this tells me something more interesting. It tells you that, look boss, if these guys are going to be black, then its neighbor should be white or deleted. Agreed? If these guys, you decided that these guys, some part of, okay, let's look at one particular guess. Deleted, and then we guessed 2 parts. This is black and this is white, right? Now look at its neighbors here. What do you know about them? Either they are part of S, or they must, all of them should be colored black. If I'm looking for an extension of this coloring, like I'm saying that either you get deleted, or this side all the vertices should get black, this side all the vertices should get white. Agreed? Now what I'm saying that if these guys have been black, then look at their neighbors. Right? If they are deleted, fine. Otherwise they have to go to the other side. In any bipartite graph, how do we start? Start from a vertex. You give him color. You give its neighbor different color. Their neighbor the different, like the color. And this is how you just propagate. So this is all that I'm trying to say, that look at the black vertices, look at its neighbors. Either they're going to be part of my superhero S, deleted, or they're made to be white. So look at the neighbors, you make it white. And what can you say about the neighbors of white vertices? They should either go to S or become black. Right? Look at the neighbors of black guys, right? Either this is what? White or deleted. And what are the neighbors of white? Neighborhood of this, either black or deleted. Right? This is it. So, and what, now if I forget this, what is this question? I've been given a bipartite graph, some white set, some black set, and what is my goal? My goal is delete some vertex from here such that whatever is white, they remain white, whatever is black, they remain black after deleted. So is it not our previous problem? This is what annotated problem was. What was our annotated problem? Let's go back. See. This is what our annotated problem was. You are given a bipartite graph, two sets, integer k, and a set of at most k vertices. You are looking for this such that this happens. Right? Now, I have a bipartite graph here. Right? This is a bipartite graph, right? Because G minus Q is bipartite. Agreed? I have a white set, I have a black set, and I'm asking, does there exist at most k minus q vertices which can be deleted, and remaining white becomes white, remaining black becomes black, because then we can put black guys here, patch it up, white guys, patch it up, and we are happy. So this is all that we are trying to do. So what we did in this problem, we reduced, given this instance, we have reduced this to 3 to the power k plus 1 polynomial time algorithm. Actually, max flow min cut computation. Okay, so please ask question if it is going above the head. We'll take a break in 5 minutes, don't worry. Long break. No? You look lost. You have to speak. Otherwise, how as a teacher do I know that you are understanding something or not? Is it not a right thing? I mean, is it not a right expectation? I mean, that we are on the same board.
Ask some control questions.
I don't know how it works in this different countries, different culture, different society. I do not know how things work, so I'm just being bit.
Choose Q.
That I will tell you. I have not told you how. I told you if someone gave you Q, how could you solve this compression problem, right? So what did we do? I said, if someone told you this, gave you this Q as a part of your input, we will come to in a minute how to get this Q. It's very easy to find this Q. But if someone gave me this Q, can I find a smaller Q if it exists? And I tell you, how do? You start with Q, you partition to 3 parts, and given this 3 part, you reduce it to a polynomial time algorithm, which finds max flow min cut. Agreed? This is the whole basic idea is this. Now, this is what happens as a compression subroutine. So whenever you're trying to design a compression algorithm, for example, what would be the compression algorithm for vertex cover? Just as you say, control question. What is the control question? This is my control question. If I give you a vertex cover problem and I give you this Q, what will you do?
Vertex cover.
Suppose I gave you the same thing, but I do not want to solve odd cycle transversal. I gave you, that's a very good question, and I'm being idiot if I will not ask this. So let's draw a picture. Here is my Q. What is the size of Q? K plus 1. And what is this? Independent set. And my question to you, is there a smaller vertex cover of size at most K?
Is it what?
I'm asking, does there exist a vertex cover of size at most K? One less than this Q. Okay? Does there exist vertex cover S of size at most K? Please feel free.
What does Q mean with regard to this?
It is a vertex cover. G minus Q. This is my Q, and V minus Q is an independent set. It's a solution. So for example, here it was odd cycle transfer. It was a large solution. It was one large solution. And we were asking, does there exist a solution one smaller? So here, G minus Q was what? Bipartite graph, because we were looking for set of vertices whose deletion makes it bipartite. So for the vertex cover, Q means G minus Q is independent set. Right? So what will be how will we solve this problem? Yes?
We can just traverse all the vertices in Q and branch, which either is still in the vertex cover for the small size, or it goes to independent set.
Yes, in some sense you are right. We could also do what we did before, but if we don't want to do that, then look, what we were trying to do, see. We decided some people are going into the smaller solution, right? And some are not. So let's make that choice here. Okay? So we decided some goes, some don't go. So go, don't go. So if we decide someone do not go, can there be an edge here? If you decide these vertices are not part of your vertex cover, then these people better be independent set. Otherwise, no, you cannot make a vertex cover of size K without containing any of these vertices. Okay? So how many such branches are here? 2 to the power K plus 1. Now this is independent. Now if these vertices does not go to these vertices does not go, then what happens to their neighbors? All of them should go. And that's it. So my algorithm is very simple. I branch, goes, and I check the people who do not go, look at their neighbors, and I say, are you less than equal to K minus go? So neighborhood of do not go. Okay? First you delete go. Okay? V minus go. In that you check, is the neighborhood of do not go less than K minus go? If it is yes, answer is yes. So isn't the problem became much more trivial now? Nothing. Right? You delete, you decided one branch, you just had to count neighbors. But here that was not enough. We needed to do even more hard work. Right? To decide whether such small number of vertices go. So this is the whole idea, that what it tries to tell you is that sometimes this K plus 1 vertices, which is your solution, could act like a help to you. It could provide you some structure in the input which you will be able to exploit for your algorithm. What was the structure here? This was independent set. What is the structure here? That outside is bipartite graph. So these are the kind of things which allows this compression algorithm to, because this is cheap. Like this is you can do this anytime, because the factor which it will add is 2 power K plus 1. This is it. So for the compression routine, this only adds some 2 power K plus 1. So it's not very expensive in terms of FPT. right? After that, you can concentrate on do not go and this, and here we needed to further branch on left and right, and then we were able to get structure. But the basic step is you decide which will go and which will not go. Go, you delete. No, do not go, you look into, you try to see what more structure do you need to exploit to solve your problem, right? Now the question, the basic question which all of you asked, who gives you this? Let me tell you, not God. We will find it ourselves. Okay. Is at least overall idea of what mean by compression is clear? Basically in compression, you are given a solution of one large, and it is nothing about k plus 1. I mean, it could be, it's just that our method will allow us to get a k plus 1, but in some problem you might get 2k, 5k, 100k, f of k, g of k, h of k. It does not matter because it's just the running time of the complexity of the algorithm would change. But the right way to think of this is a help, or it provides more structure to my input, and that's it. Now, for example, I'll give you from where can we get this Q for vertex cover. Does anyone of you know approximation algorithm for vertex cover? Yeah, factor 2 approximation. Gridly find maximal matching, take both endpoints. It's a factor 2 approximation. If people know, right? So what I do, I find this factor 2 approximation very easily, gridly maximal matching endpoint. I check, is it more than 2k? Strictly more than 2k? What is your answer then? Answer is no. Because if it has a vertex cover of size at most k and it's a factor 2 approximation, it should return me a vertex cover of size at most 2k. Great. Now I have got my Q, right? 2k, this. I could do whatever I was doing here, is just that. Then my algorithm running time will be 4 power k plus 1 or 2 power 2k, right? I could solve my vertex cover problem using this. I get this vertex cover from approximation, go, no go, and do. That's it. So we will be able to do this in 2. Now, but why approximation algorithm? For odd cycle transversal, I don't know any approximation algorithm whose running time is like constant. The best known approximation is square root log n. Things can become difficult, but there is one way to get this Q. There could be various thousand ways of getting this Q. Okay, but here is a cheap way. Right? So this is what I was trying to tell you, that if you get, this is the problem which you will get and which we know how to solve in polynomial time. Now this step, it has nothing to do with odd cycle transversal. It is about any minimization problem. Free. Okay. Tell me one thing. It's a very two-liner, okay? It's literally a two-liner which all of us will understand. I think it is best explained with a box. So suppose this is my graph and its vertex set is v1, v2, vn, some arbitrary order. Let's call graph gi graph induced on first I vertex. Okay? Okay. Let's write down gk plus 1, which basically means graph induced on first k plus 1 vertex. Okay? Can you find Q here? In this graph, can you find Q? No? Yes? Yes. What is the Q? Huh? What? Exactly. So Q is V1, V2, Vk plus 1. Let's do it for vertex cover. Then we will see why it works for odd cycle transversal, any problem if it is a great. Just now I gave you an algorithm for vertex cover. What will it test? So here's your algorithm. This is an input. It takes three things, G, some Q and parameter, and decides whether you have this compression algorithm or not. We gave him because he needs Q. Without that, he doesn't know how to work. So I gave him, it can output two things, yes and no. It says it does not have a vertex score of size k. What can you say then? Can G have a vertex score of size k? No. If for a small graph I can't find a vertex score of size k, induced graph, do I hope to find a vertex score of size k for the whole graph? Absolutely no, because if I had a vertex score of size k for the whole graph, look at its induced here, that is also a vertex score of size k. So if this guy says no, I don't even go further. I say G comma k is a no instance. For simplicity, it also gives you smaller size. Okay, it also tells you, if it says yes, it returns you some s of size at most k. Okay, it returns you when it says yes. Now I want to make it for g k plus 2. What is the q for g k plus 2?
Yes.
Right? Feed him again. It says yes or no. No, no, yes. I will go to k plus 3 and S union vk plus 3. Feed him, yes and no. K plus 4. I keep doing this. How many times do I need to do? N times. And I'm done. Odd cycle transversal? Yes. Same thing. I start with k plus 1. Is it an odd cycle transversal of size k plus 1? Yes, delete it. Graph is empty. It is bipartite. Whatever you feel like. Maybe we can leave two vertices for that. Maybe we can start from k plus 3. Only delete, or maybe, yeah, k plus 1 vertices, 2 vertices. They are bipartite because in the best case they can be edge. Keep doing this, keep doing this. Isn't it for free? And I call it free because you only have to apply n times the same algorithm. Not even FPT time, it's pure polynomial n times. So this is why it is for free. Now, it seems a bit counterintuitive, but somehow this has been the test bed for most important problems being solved in parameterized algorithm, like multi-cut, directed feedback vertex set, some C power k algorithm, and many, because it just provides you that structure in the input which we can exploit, and it is for free. It is absolutely for free, right? So this is why I said that blah, for every I we find a set Si of size k such that Gi minus Si is bipartite. For Gk, this is a trivial solution. For Si minus 1, if Si minus 1 is known, this Si minus 1 Vi is a set of size k plus 1, whose deletion makes Gi bipartite. Now you use my compression algorithm. So the total running time of this algorithm is this much, 3 to the power k times mod 3 to the power k dot k times this for each compression routine. And how many times we are repeating this? N times. So this is my algorithm. Okay. So this is the algorithm, right? So more important is a technique. This is how you do iterative compression. You formulate a compression problem, you do some yes and no, and based on that you try to formulate an interesting problem which either you can solve in polynomial time or you might need an FPT time. For vertex cover, it was just the counting of neighborhood. For odd cycle transversal, we had to make 2 more partition and reduce it to multi-cut, like max flow min cut algorithm and kind of things. Now the fun part is, this is where the Matroid starts. This algorithm we can encode in a small data structure with polynomial in k bits. This algorithm, and that is the kernel of the problem. But that requires matroids, which we will see in the second lecture. I think we'll stop here for the first lecture.